Okay, good morning, everyone. How are you today? Did you have a nice weekend? Well, I hope you did. You know, it's strange times we live in, but you should still get outside and enjoy yourself when you can. So I hope you are enjoying yourselves. Uh, I had an okay weekend, and I thank you for asking. Okay, happy birthday, Quinn. Happy birthday to you. Okay, it's nice to see everybody. And so we're going to get started with chapter 8 today. Before I do, let me ask you, do you have any remaining questions about the lab exam from last week? As you know, the class average was about an 89%, so it was a very strong average, and most of you did very well on it. So I don't personally have any concerns with it. So do you have any questions at this time?
Yeah, for some reason my grade disappeared on I can't see that test for the grade on class marker. It only shows exam one for me.
Matt, when is the last time that you tried to look at your grade?
Um, I think it was on Friday or Saturday, because I've been in New York for the past 4 days, so I haven't
Okay.
looked since I got back.
Okay, I'm going to ask you after today's class to please check again because there was a computer setting that got switched, and I think I've taken care of that. So try again, and if you still can't, please email me, okay?
All right, no problem.
Okay. So Quinn, you have a question about your specific exam. I'd ask you to send me that kind of question through email since we're on a public forum right now. Okay. All right. Any other general questions or concerns? Okay, gang. Welcome back. Let's see what we have in store this week. We have to cover chapter 8 this morning and hopefully at least start chapter 9 a little bit. So you recall from last week, we were talking about some pretty heavy physiology in the nervous system, talking about the nerve impulse, which is also the same thing as an action potential, which is also the same thing as an electrical signal, a movement of ions back and forth across the plasma membrane of a neuron. We're going to switch gears and go away from that intense physiology a little bit and talk a little bit more about the basic anatomy of the nervous system, which is mainly the focus of chapter 8. Okay, so we're going to do a little show and tell for you today about some of the major anatomy of the nervous system. Okay, so bear with me. What we're going to do is go back to our Microsoft Word document and start taking some notes. Okay. Okay, so the chat window is up. Okay, so you can reach me if you need to. And the Word document is also up. Okay, so chapter 8 begins basically on page 127, 128. Okay? So when we talk about the nervous system, we recall that we talk about the central nervous system and the peripheral nervous system. So let's redefine these things, which I know you already do know about. Okay. The nervous system is made of two subsystems. That would be the central nervous system, okay, which again is primarily made of the brain and spinal cord. And the peripheral nervous system, which is composed of the nerves that come off the brain and spinal cord and spread throughout the rest of the anatomy of your body. Okay, it's only through the peripheral nerves, right, that you can have sensations in your big toe or your little toe or your fingertips, right? Or at the surface of your skin. It's only through those nerve endings that we know what's happening at the surface of our bodies. Okay, now the peripheral nervous system, as you see from the flow chart on page 128, figure 8.1, okay, can actually be broken down into some other areas. We have the sensory input. Okay, so when we talk about sensory input, we're talking about nerve endings that are designed to receive stimuli from the external world in some way and deliver that information into the central nervous system. And then we also have the motor output, which is made of neurons that deliver information from the command and control center of the body, which is your brain, typically your brain. Okay, so you hear some music playing, you listen to the music for a moment, and your brain says, oh, that's pretty cool. That's pretty catchy. I like that song. I think I'm going to move my body closer to where that speaker is so I can hear the music better, right? So to respond, first, to know that there's music playing, that's going to involve the sensory input, but then to respond to that sensory input in a way which you move your body closer to the loudspeaker transmitting the sound, well, that would involve the motor output in the purple section of figure 8.1, page 128. Okay, so the motor output is made of neurons that transmit instructions from the brain. Okay. Now, I don't want to get too far down into the weeds because this is more of an A&P topic, but we can start breaking down the motor output into subsystems as well. And I will highlight two of those areas. I'm going to jump to the somatic nervous system at this point, okay? So we have the somatic nervous system, okay? That's going to involve nerves that carry information to and from the central nervous system. They are part of they're part of communicating with interneurons from the sensory input. Okay. Okay, so we have the somatic nervous system. This is made of nerves that carry info into the central nervous system and allow the body to respond via the motor pathways. And then we have the autonomic nervous system. The autonomic nervous system is what that word suggests to you, autonomic, automatic, okay? This part of your nervous system is responsible for regulating involuntary and unconscious activities, such as your heartbeat, such as your heart rhythm, such as the digestive system activity, you know, how well your intestines will contract with the smooth muscle to move material through the intestinal system. All of these things are automatic and largely beyond your conscious control. Okay. Now, the autonomic nervous system can be broken down into subsets, which I bet you heard about a long time ago in maybe health class in high school. Okay, so we'll break this down even further. And the autonomic nervous system can be further broken down into the sympathetic nervous system and the parasympathetic nervous systems. Okay, the sympathetic nervous system is often associated with the fight or flight mechanism that you may have learned about in health class in high school. You know, whether you're going to stand your ground and fight or you're going to flee from a danger. So the sympathetic nervous system prepares the body to respond for an emergency. The so-called fight or flight. Okay, so it ramps up the body. And obviously there's going to be plenty of times when we don't have a need, thankfully, to fight or flee, but there's going to be a time to rest and digest, a time to conserve energy, and that's going to be the job of the parasympathetic nervous system. So the parasympathetic nervous system will maintain a state of rest and digest. Okay, it's pretty much the exact opposite of the sympathetic nervous system. Okay, so please understand that all these designations that we're talking about here and defining in your notes, these are designations that human beings have artificially created. Your brain doesn't think of itself as sending information along a parasympathetic neuron or a sympathetic neuron. Your brain doesn't know or have these designations, and frankly, it doesn't care about them. The body has the anatomy it has, and it works the way it works. The names are artificial labels that human beings have ascribed to things that we've observed over time. Okay? All right, so that's just a broad overview of figure 8.1 on page 128. Do you have any questions before we continue?
No, just a comment. If people don't know, there is ways to train the sympathetic nervous system to react kind of in a way to your favor. So it's what the military does for training for high stress situations. So you don't have that kind of lock up and involuntary response, or you can actually just make it to only fight instead of flight because you just train your body to it.
Sort of a conditioning that allows you to.
Correct. Yeah, they gotten to the point where through like sim rounds and everything where you can have virtually live fire drills and room clearings and stuff like that, so you know how to react, and your body, you don't have that fight, flight, or freeze, and you don't ever freeze or really run away. So you don't really go into that sort of sympathetic nervous system where you're not in control. It's just through rigorous training and getting conditioning as close to the environment you're going to be in.
It makes a lot of sense. Thank you, Matt, for sharing that. I'm sure the military definitely has an interest in having its soldiers being able to control that response. So absolutely. Okay, any other comments or questions? Okay, gang. Okay, so what we're going to start with here is talking about structures that protect the central nervous system. So this goes to some of the language, some of the reading that you have on pages 128, 129. Okay, structures that protect the central nervous system, the CNS for short. Okay, so your book it is a decent textbook. I mean, it is. I mean, it's always possible to get books to go in greater detail, but it does show you some things here. So first we'll talk about the obvious things that protect your brain and spinal cord, right? We're talking about things that protect the brain and spinal cord. I don't think it will be a shock to you to suggest that the bones of your skull protect your brain and the bones of your vertebral column, your vertebrae, protect your spinal cord. So we'll put that down first, the skull and the vertebral column protect the brain and spinal cord. And you certainly know what those things are. I mean, you know what the anatomy of the skull and vertebral column kind of looks like, if from no other thing than doing the lab activity of last week, where you had to do some of the basic bone anatomy and muscle anatomy from last week's lab. Okay. Number 2 would be the meninges. Okay. So this is sort of a loaded word here because I'm sure you've heard of things like meningitis. So let's talk about this. Meninges. When you hear the word meninges, what we're talking about is a group of 3 layers of connective tissue. Okay, each layer of connective tissue is a meningeal layer. We're talking about 3 different layers of connective tissue that wrap themselves around the brain and the spinal cord. Okay. So meninges refers to 3 layers of connective tissue that wrap around the brain and spinal cord. Okay. Now your book, unfortunately, doesn't really have too much in the way of good visualization on that. For that, you need some other resources. So what I'm just going to do is list out the layers for you, and then I'm going to show you an image from Google Images that gives you a little bit of visualization on what these layers of tissue actually look like. Okay, so let's define them, and then I will show you a picture about this. Okay, so the outermost layer of the meninges, and by outermost, I mean the layer of tissue that is furthest from the brain. Okay, the layer that's furthest from the brain is called the dura mater. This is the layer furthest from the brain. Okay, it is the outermost layer. All right. Next, we have the intermediate or middle layer, and that's going to be known as the arachnoid layer. Okay, it has the arachnoid layer, as you look at the layer and the surrounding anatomy, has some kind of spiny projections to it that sometimes resemble kind of like a spider web appearance. So hence the word arachnid for spider or arachnoid. Okay, so it can at times be associated with anatomy that has kind of a spider web-like appearance to it. But at any rate, this is the middle layer of the meninges. And then we have the layer of connective tissue that is physically closest and in intimate contact with the surface of the brain. That's the innermost layer, and it's called the pia mater. Okay. All right, so I'm not going to show you a picture that's gross or anything. What I mean is don't worry about what I'm about to show you. It's not gross. It's simply an artist's drawing of some of the anatomy of the brain. Okay, so here we go. So on your screen at this time, you should see a picture of a cross section of the skull, right? And hopefully, I honestly don't know if you can see the motion of my mouse or not on your screen. At any rate, up here, you should be able to see the cross section of your skull, right? This open porous area of bone tissue, okay? If you go over to the right side of the picture, you should see the dura mater, which in this drawing has sort of a grayish appearance to it, okay? Underneath that and the middle layer is the arachnoid mater or the arachnoid layer, okay? In this picture, it is colored sort of a pinkish color, and you notice the projections of pink that come off of it, hence the spider web-like appearance to it. Okay, obviously these are color-coded in the drawing so you can identify them. The arachnoid mater does not have a vibrant pink appearance in the body, nor does the pia mater, which is the innermost layer, have a green appearance. But okay, so the pia mater is the innermost layer, and you can see it there. And you notice the pia mater runs along these brown convolutions, which are actually the outer border of your brain where your cerebral cortex would be. Okay, so once again, we have the dura mater, we have the arachnoid mater, and we have the pia mater. And these three layers are made of connective tissue, and their primary function seems to be physical protection of the very delicate brain tissue. Okay? All right. Folks, do you have any questions about that? Alyssa, what is the subarachnoid space made up of? It is made of some open space with some fatty tissue in there. Okay, there's a pocket of fatty tissue in there that is used as an energy reserve for the cells of the brain. Okay, other questions? Maybe someday you will have an opportunity or a requirement to take a neurology course. And obviously you'll go into things very heavy in that course, and I think you will find it demanding and interesting at the same time. Okay, so, all right, so now we know that there's these things called the meninges, okay? And so can anybody tell me, I'll put a question mark in your notes here, what is meningitis? If you hear the phrase meningitis, what is that? What does meningitis mean? Okay, Alyssa, you say a brain infection that can lead to brain inflammation. Okay, Alyssa, you said some good stuff there, and you also said some stuff that's not quite right, okay? The fact that the word meningitis ends with this itis tells you it's inflammation, okay? So meningitis is inflammation of the meninges. That does not necessarily mean there's an infection, although it could mean that. Okay, so infection and inflammation are not the same thing, but they are two sides of the same coin. Okay, so be very careful. Infection and inflammation are not identical, but they're certainly related to each other. So meningitis is inflammation of one or more layers of the meninges. Okay. And so what can cause, what our next question should be, what can cause this inflammation? Okay, Matt, you say it can be bacterial or viral. I like that. That's a lot of good stuff that you said there. Okay, and Alyssa, you had said a brain infection. So certainly if you have bacteria where it's not supposed to be, that could be a brain infection, or a virus where it's not supposed to be, that could be a viral infection. Let me broaden this a little bit, folks. Basically, any category of microorganism that modern science is aware of could in fact create inflammation, okay? Any category of microorganism is capable of producing inflammation. inflammation. So that would include bacteria and viruses, which you've all stated, but please don't count out things like fungi, right? You could have a fungal infection of the meninges, which creates the inflammation. You could also have protozoa. Okay, I don't know if any of you have watched the news lately, but I think there was recently a case of someone being killed in Florida from a brain eating amoeba. Okay, an amoeba is a type of protozoa. Okay, so if you studied some amoeba in your high school biology class under the microscope, that's the kind of critter I'm talking about. There are different species of amoeba, and some of them are actually dangerous to animals. Some are dangerous to human beings. And there is a variety of amoeba that, if you are unlucky enough to get it into your brain region, it will literally start to eat the brain. And when that happens, it is almost always lethal. It almost always kills. Okay, so bacteria, viruses, fungi, protozoa. This is a short list of things that could, in fact, Quinn, you asked, why is it always Florida? Well, I don't know. I mean, obviously, Florida is a coastal state, and so there's a lot of swimming going on down there and a lot of water sports and a lot of water activities. It might just be a weird coincidence, but certainly anywhere that you have possible water contamination, you could potentially get this. Cases have been documented of children playing in muddy puddles and unfortunately picking this up and dying from it. Okay. Okay, Jennifer, thank you for sharing that. You have a friend's son who was diagnosed with bacterial meningitis at the age of 8. It almost killed him. Oh dear Lord, he lost his legs and multiple skin grafts. That is absolutely horrible. I'm very sorry to hear that. A lot of sad stories out there, folks. Never, never, never underestimate microorganisms for what they can potentially do. That's why we've really got to take this coronavirus situation seriously, as hard as it is to stay away from others at this time. Okay, Quinn, you ask, is that what happened with mad cow disease? Okay, so let's just knock that one down real quick. Mad cow disease, okay, so in parentheses in your notes, I've listed bacteria, viruses, fungi, protozoa. These are microorganisms. They're categories of microorganisms that can potentially cause inflammation of the meninges and hurt you really, really bad. Okay, so the question was, what can cause this inflammation? So I say any category of microorganism. Also, misfolded proteins. Okay, you know about proteins at this point from having taken this course. Misfolded proteins are called prions. Okay, they're called prions. This is what's responsible for mad cow disease. And yes, it can not only create inflammation of the meninges, but it can actually inflame your entire brain. Okay. All right. Okay. So one other thing you need to be aware of, folks, okay? So we're saying what can cause inflammation, and we're defining all these microorganisms, and in a peculiar case called a prion, which is responsible for mad cow, okay? But I also would like you to be aware that cancer can also create meningitis. Okay, so if you are unfortunate enough to be developing some sort of brain cancer, that can also create meningitis, and in fact, meningitis might be the first warning that there's something wrong in your body. Okay, so obviously the laundry list of things that we're putting down here is getting bigger and bigger of the number of things that can potentially cause meningitis. Okay, so another question, and then we'll move on from this topic. Let me ask you this. Can all cases of meningitis be cured with antibiotics? Can all cases of meningitis be cured with antibiotics? Okay. Okay. Matt was very quick to say no. Do you agree with him? Okay, good. I'm glad to hear that, right? Antibiotics, as a general term, tends to mean antibacterial diseases, okay? Now, it gets a little bit more detailed than that, and, you know, take a microbiology course someday. I'll be happy to tell you about that. But suffice it to say, you know, things like penicillin and so forth, those tend to be primarily antibacterial medications. So if you had meningitis caused by a bacterial infection, there's a good chance it could be controlled with an antibiotic. But if you had a fungal infection, most of our common antibiotics are not going to be successful. Certainly if you had viral meningitis, our antibiotics are not going to be successful. Okay, so you don't want to get sick with this, but if you have to get sick, get sick with a version that we have a medication that can treat it. Matt, what are the other forms of treatment if not bacterial? Okay. Well, Matt, if you have viral meningitis, there is no treatment to cure the viral infection. All you can do is support the body with steroids to reduce the inflammation and provide supportive and comfort care to the patient, and hopefully they will survive it. But there is no antiviral medication that can be given. If you do have a fungal infection, there are some antifungal drugs that can be given, but sometimes the side effects of them are as bad as the disease itself. So it's a little bit of a gamble what you treat with. And if you're unlucky enough to have a protozoal inflammation, such as I was suggesting from the Florida case, we do not have good medications to treat that, which is why many cases end in death for the patient. Okay, folks. So don't let your children splash around in muddy puddles. It might seem safe, but it probably is not safe. Okay, I know we take all the fun out of childhood, but you have to be aware of these things. Do you have any other questions about meningitis at this time? A little dirt builds character. I generally agree with that, Matt, very much. And please understand, right, the vast majority of time, for every million children that splash around in a muddy puddle, maybe only one of them is going to be unlucky enough to get something nasty that hurts him or her, right? So we can't protect our children from everything. Okay, let's continue. The broad topic here is structures that protect the central nervous system. So the skull and vertebral column is pretty obvious. The meninges, we've just shown you what the meninges are. Next, we have the third thing, which is the cerebrospinal fluid. Okay. The cerebrospinal fluid is a liquid that's manufactured out of your blood plasma. Okay, if you think about it, every liquid in your body, whether it be urine, cerebrospinal fluid, the tears on the surface of your eyeball, your lymphatic fluid in your lymphatic vessels for the lymph circulation, every fluid gets its water from your blood plasma. Okay, so the cerebrospinal fluid is no different. The volume of the cerebrospinal fluid is from the water of your blood plasma. It's made from that source of water. Okay, so this cerebrospinal fluid is a water-based fluid. It fills the space between the arachnoid layer and pia mater layer of the meninges, and it also fills up any internal cavities of open space, both in the brain and the spinal cord. Water-based liquid that fills the space in between the arachnoid and pia mater layers of the meninges, and fills up open spaces in the brain and spinal cord, right? I mean, it would probably be the butt of a joke to say that some people have hollow space in their brain, but that's true. We all have some open, hollow ventricles, spaces, where there really isn't cellular material. There's no neurons and glial cells. It's simply open space, and that open space is not maintained as open air, but as a space for liquid to fill up. Anytime there's an open space, cerebrospinal fluid is going to be in that space. Okay. All right. So at any rate, the cerebrospinal fluid, which we're referring to, it does a number of things for us. Okay, this liquid provides a sort of shock absorption characteristic. Okay, it has shock absorption features. Think about, you know, I mean, it's kind of a ridiculous analogy, but if you had to fall down flat on your face, would you rather fall down flat on your face on the macadam of your driveway, or would you rather fall down flat in your face into the water of a swimming pool? Obviously, the water of the swimming pool is going to be softer. Okay, so the water of the cerebrospinal fluid actually has a shock absorption property that helps absorb physical shock and reduce the trauma to the surrounding brain tissue. Okay. The cerebrospinal fluid also supports the brain and spinal cord. Believe it or not, your brain literally floats on a very thin layer of cerebrospinal fluid between the brain and the bones of the skull. It literally floats in that space. Okay. Okay. The neurons of the nervous system are incredibly powerful cells, and they do some amazing things, but they are also horribly delicate cells. Okay, so literally the neurons that make up the brain are so delicate that if the brain were to physically rest on the bones of the skull, the brain's own weight would crush the neurons at the base of the brain and kill them. So to avoid that, Mother Nature created a scenario where there's a little bit of liquid in there, just enough to reduce that stress of the brain resting on the bone of the skull. It literally floats in that liquid. Okay, and finally, nourishment, which is to say that the cerebrospinal fluid is water-based, and we know that water is an excellent solvent, and as a solvent, it's very good at distributing nutrients into the cells that make up the tissues and organs of our body. Okay, so that would be the cerebrospinal fluid. Okay. Something occurred to me as I was typing this note out, something back up with the meninges that I should mention. Okay. I don't know how many of the gals in the room have had children or experienced childbirth themselves, but I will ask the ladies online if you have ever actually experienced or talked with your mothers and grandmothers about something called an epidural. Have you ever had an epidural, or talk to someone about an epidural. Okay. What is an epidural during childbirth? Okay, Matt, you say your wife did. Okay. So, all right. Okay, Jennifer. So you've experienced it, right? Okay. In other words, an epidural is when the physician administers some pain medication to control the pain during childbirth, and now you know what's happening. In other words, the pain medication is literally being put epi, meaning on top of, okay, on top of the dura mater. Okay, here's the dura mater. Okay, so this would be the location that an epidural would be administered, where some numbing medication would be applied to the surface of the dura mater to reduce the pain during childbirth. Okay. Let me type that out here into your notes. This is when a medical doctor gives a pain relieving medication on top of the dura mater. Okay. This is when a medical doctor gives a pain relieving drug on top of the dura mater. Okay. All right, gang. So, you know, there's definitely practical implications for the things we're talking about here today. Okay. That's number 3, the cerebrospinal fluid. Okay. The final thing I want to talk to you about for structures that protect the central nervous system is the blood-brain barrier, number 4. Okay. The blood-brain barrier is described to you on page 129. Okay, and your book just gives you some words here. Okay, but the blood-brain barrier is a network of capillaries. Can anybody tell me what a capillary is? Does anybody know what a capillary is? We haven't talked about it in our course yet. Okay, Pete, thank you for participating. Okay, Pete, you will definitely find capillaries in the lungs, but you're going to find capillaries everywhere. So it's not specific to the lungs. And it's not really specific to airflow either, but thank you for trying. Okay. But yes, everywhere, Quinn. Okay. Capillaries are tiny, tiny blood vessels. And obviously we have blood vessels throughout our internal anatomy everywhere. Okay. Now we're talking about the capillaries that are specifically in the brain area. So the blood-brain barrier is a network of capillaries. Okay, so let me put in parentheses, tiny blood vessels. Okay, we're going to be talking about in a future chapter. That's right, Matt. Okay, a network of capillaries that regulates what enters and exits the brain and spinal cord. Okay, in other words, think of the blood-brain barrier as a checkpoint, as a security checkpoint, as a boundary that helps regulate what content from the bloodstream can leave the bloodstream and enter the cells of the brain and spinal cord. So in that way, this network of capillaries is a safety checkpoint, a safety and security checkpoint to regulate what kind of molecules can access the brain tissue. Okay. So this blood-brain barrier is meant to be protective for us, but ironically enough, with modern medicine, sometimes the blood-brain barrier is actually frustrating to medical doctors, because in some cases, the actual anatomical makeup of this blood-brain barrier can sometimes block or prevent life-saving medications that need to be administered to the brain from getting into the brain. Okay, so this blood-brain barrier was created obviously by Mother Nature to protect us, but there are some cases where it actually gets in the way and makes treating a disease more problematic or more difficult. Can in some cases frustrate medical doctors by blocking medications from entering the brain and spinal cord. Okay. All right. So, you know, if you have a situation, you know, maybe it's cancer of the brain, maybe it's inflammation, maybe it's meninges, something where you really need to get a medication into the brain tissue to solve a medical problem, but the blood-brain barrier blocks it from getting in. You know, there aren't many good options at that point. So at that point, to get, you know, if you have a drug that has to get in there, the only recourse might be literally to have brain surgery, open up the skull and apply the medication on the surface of the brain to get the brain in there. Okay, so obviously that's not a good thing. I do want to mention to you that there is a similar barrier that we don't call the blood-brain barrier, but we call the blood-retinal barrier in your eyeball. Okay. Okay. And we will be talking about the retina in chapter 9 coming up. But you know that the retina is made of nervous system tissue. Okay, so not only did Mother Nature see fit to design a network of capillaries that protects the brain and spinal cord, it also considered important to design a network of capillaries to protect the delicate nervous system tissue of the eyeball, and that's what's called the blood-retinal barrier. The blood-retinal barrier also makes it very difficult at times to treat certain, you know, vision diseases. You know, macular degeneration, diabetic retinopathy, things like this can be very challenging to control with medicine. And some of the medications just don't get into the tissue very well through the bloodstream. Okay, so that's why that depending on certain medical conditions, sometimes you actually have to go to a specialist. And, you know, this might be a little bit gross, but it is the case that sometimes you have to sit in a doctor's office and they literally stick a needle through your eyeball to inject a medication back onto the surface of the retina to help treat your disease, whatever it might be. Okay, so that is sometimes necessary and kind of unpleasant, right? But it is necessary. Okay. Any questions about that? Alyssa, you ask, is that why Excedrin, which has caffeine, works better for extreme headaches than regular Tylenol? I don't think we can say that, Alyssa. Everybody's body is different, right? Your body is genetically different from mine and genetically different from everybody else's in class. When I say you're genetically different, we're genetically distinct from each other's. What I mean by that is because you have different DNA than me, the biochemistry of your body is different than mine, which is why one medication might work for you better than a different medication. Okay, so there's a lot of things that we honestly can't explain about that at this time. Jennifer, I treat capillaries on the face with an IPL laser as part of my profession. Not sure if this is related. Well, it's certainly related to the idea of capillaries. Okay, is this treatment, Jennifer, for some sort of cosmetic blemishes, or is there something else? Okay, cosmetic blemishes. Yeah, okay, fair enough. Okay. Pete, you're asking me, are ethnic genetics the same? Are you asking me about people of the same race, like Caucasian or blacks or things like that? Is that what you're asking? Yeah, okay. Well, let's put it this way, okay? Generally speaking, all African Americans would probably be more similar in makeup with each other, with other African Americans, than they would be with somebody from the Asian community. But that being said, we're all a global community of human beings, and we do share more DNA in common than different. Okay, so we want to be careful not to be. These things can be politicized and idealized in evil ways that we need to be careful about. Okay. Any other questions? Okay, gang. All right. So that's your quick introduction to structure that protect the brain and central nervous system. What I'm going to do next is start a journey describing some of the brain anatomy that you see in the next several pages. And your focus point, probably for right now, should be page 130. Okay. On page 130, you have figure 8.3. And so we're going to talk about some of this brain anatomy that you see here at the bottom of page 130. So let's talk about brain anatomy and overview. Okay. All right. So, okay. Well, what can we say? There's plenty of things we could say, okay? But let's talk about the topmost section of the brain. This is going to be your cerebrum, okay? So please try to put an eyeball on things as we highlight them in your notes today. Cerebrum is the first term on the top right side of figure 8.3. Okay, their cerebrum is the largest part of your brain, and it's the topmost portion of the brain. Topmost, largest portion of the brain. Okay, it is separated into two hemispheres, right? And if you don't believe me, take a look at figure 8.5 on page 132. And as you look down on the surface of the cerebrum, you can see that there's this line coming down the middle of the brain. And you can see you have a left side of the brain and a right side of the brain. That's what I mean, that the cerebrum is separated into two hemispheres. Okay. Okay, Quinn. Keep working it. If you need to log out and log back in, please go ahead and do that. Okay. So the cerebrum is the largest portion of the brain. The cerebrum is the portion of the brain that gives us our humanness. Okay, portions of the cerebrum give us our ability to speak in a language, English or Chinese or whatever language you might be speaking, German, right, Italian, Spanish, whatever it might be. Those abilities to evoke language and use language are contained within substructures of the cerebrum. Our ability to think, to imagine things, to work out mathematics, to daydream, all of these human attributes and characteristics are warehoused in the anatomy of the cerebrum. Okay, so I will say that the cerebrum is the warehouse, and I'll use that lightly in quotation marks, is the warehouse of our humanity, of our human experience. Okay, portions of the cerebrum allow us to speak, okay, allow us to imagine things, allow us to daydream. Okay. Quinn, is this where our personality is formed? I think to a large extent, yes, although exactly obviously how that happens is still a huge mystery. I don't know if we'll ever get that figured out. Okay, generally your ability to think higher rational thoughts, to engage in mathematics. Okay. All these sorts of things are stored in the cerebrum. And I will also mention, yes, Matt, that's where the two hemispheres come in with the left-sided and right-sided ideas. Yeah, but like with most generalizations, that might be an overgeneralization, but that is where it comes from. The cerebrum is where you get your sense of self-awareness, the idea that you actually exist, the idea that you know you're sitting in a room somewhere right now taking a course online. You know you exist, you're self-aware, you're self-conscious. That comes from properties and attributes of the cerebrum. Okay? Your own self-awareness is stored or emanates from the cerebrum. Okay? Think about that. You may have seen an animal. Typically, I think typically dogs. I've seen dogs that have looked in a mirror and they barked at themselves because they thought they were looking at another animal. They did not understand they were looking at a reflection of themselves, which kind of suggests a little bit that maybe the dog is not even aware of its own existence. It doesn't have that self-awareness to its mentality. Okay? But clearly, when you and I look at a mirror, we know we're looking at a reflection of ourselves. We are self-aware. So animals are pretty close, depending on what animal you're talking about, Pete, obviously certain animals are extremely self-aware, think about chimpanzees and things, okay? But, the more distant an animal you're talking about, the less likely they are going to be self-aware. And when it comes to bugs, bugs do have rudimentary nervous systems. They certainly have neurons in them, but they typically only allow that bug to do something that allows it to interact or respond in the environment. There's no evidence they have a sophisticated sense of self-awareness. Okay, any other questions right now? Pete, are they self-aware when they're surviving and doing their own thing? I can't answer that for you, Pete. I don't know. I don't. So if a bug were to run away from a dangerous chemical, is it self-aware? I kind of doubt it, because I think what it's doing is detecting a substance that creates some sort of pain or chemical pain sensation in its small little body. So it's running away from something that hurts it. But I wouldn't be comfortable saying that that's the same thing as being self-aware. Okay. Okay, anything else? All right. Let's continue here. I would point out that the top, so the cerebrum is the topmost part of your brain. Could self-preservation be considered self-awareness, Matt? I think we could argue and debate that for quite some time. I'm not uncomfortable with what you're suggesting, but I'm also not sure that it is the same thing, if you see what I'm saying. So the cerebrum is the topmost part of the brain, but if we look at the topmost part of the cerebrum, that's also given a special name. The topmost part of the cerebrum is actually called the cerebral cortex, okay? The topmost part of the cerebrum is the cerebral cortex, okay? So the cerebral cortex is the top layer of the top part of your brain, which is the cerebrum. So the cerebral cortex is the top layer of the cerebrum. Okay. And so this cerebral cortex has been mapped by scientists over the years. And by mapped, I mean that we have a general idea of what areas of this top layer are involved in different processes of the body. And so I bet you learned about this also in health class, because it's a common thing to be in courses that are taught. And so let's take a look at the cerebral cortex lobes, 4 lobes of the cerebral cortex here. Okay, and what I'll say is, first we have the frontal lobe. Okay, and you can see that color coded as sort of a yellow section of the cerebral cortex on figure 8.4, page 131. So the frontal lobe, this is an area of the brain that contains a collection of neurons, which is referred to as Broca's area. And it's in this area of your brain that your ability to speak comes from. Okay, so the frontal lobe contains a subset of neurons called Broca's area, which is involved in your ability to speak. Okay, so if there was an unusual injury and a head trauma of sorts in a car accident where a person woke up and they seem to be having a hard time speaking or enunciating words, a brain scan might in fact reveal some sort of inflammation or trauma to the frontal lobe of the cerebral cortex of the cerebrum. Okay. In addition to the frontal lobe, obviously we have the parietal lobe. Okay, the parietal lobe is at least in part responsible for processing your taste sensations that you get when you eat food and consume, drink of various kinds. The intensity of the experience and the different sensations of the food that you might be taking in, that's processed at least in part in the parietal lobe section of the cerebral cortex. We also have the occipital lobe. The occipital lobe is famous for its ability to process vision. So the occipital lobe, will receive information from the major nerve fibers coming out of the back of your eyeballs, and it will allow your brain to interpret what you are seeing. Okay, so you're looking at a beautiful rose bush sitting outside your window. The occipital lobe is going to be involved with processing that information. Okay. So again, if you were in an unusual car accident and somebody wakes up and they're blind or having a hard time seeing properly, and the doctor looks at that person's eyeballs and cannot see any trauma or damage to the eyeball or the optic nerve, the next logical thing that they will check is to do some sort of brain scan and see if there's been a bruise or inflammation of some kind of thing on the occipital lobe. Okay, and then we have the temporal lobe. The temporal lobe is responsible for your sense of smell. Okay, so when you smell the aroma of a freshly cooked meal or the aroma of perfume or whatever it might be, that's going to be handled in the neurons of the temporal lobe of the cerebral cortex of the cerebrum. Okay. Okay. All right, gang. Any questions so far? Jennifer, you have a question about a brain pill like Noriva? Um, I'm not familiar with that medication, Jennifer. Can you tell me what it's for?
Hi, it's just a pill that you can get in like Giant. It's like for brain performance.
Okay, so it's an over-the-counter sort of supplement of some kind?
Yes.
Okay. Well, I honestly, I would be guessing if I told you yes or no. Um, Without knowing what the chemicals are in the pill, it's really hard to say. But it is possible that if there is any positive impact of this medication, it could be simply due to the fact that it helps your blood flow in the brain. So if you enhance the blood flow even a tiny percentage, that might be enough to allow your brain to function a little better. So it's possible, but I couldn't really say either way.
Okay, thanks.
Quinn, did you have a question? Okay. Folks, remember when you talk about supplements and over-the-counter kinds of medications, those sorts of things are typically not regulated as stringently by the Food and Drug Administration as medicinal drugs are, which is not to say that they're unsafe. They tend to be safe, or else they would be taken off the market. But when you have an over-the-counter supplement, there's not a large body of medical evidence to suggest that it does or doesn't do what the advertisers are suggesting. Okay, so just be aware of that. And let's be honest, there really is such a thing as a placebo effect. Sometimes you take something that's really not doing anything for you, but you feel like it's doing something for you, so you feel better. That's a legitimate effect. That does happen. Okay. Quinn, if you need something, please type it out. Okay. All right. Let's continue. I also want to draw your attention to the corpus callosum. Okay, the corpus callosum. Okay, I'm going to make this number 2. The corpus callosum. Okay, take a look at that picture on page 130. The corpus callosum, you can see, is underneath the cerebrum. Okay, and the corpus callosum is a band of tissue. Okay, it's kind of like a cable, if you will. That helps electrical signals from one hemisphere of the brain travel over to the other hemisphere of the brain. So you can think of it as a telephone cable between the left and right hemispheres of the brain. Okay. And so of note here is the fact that for some unfortunate folks that have seizure disorders like various forms of epilepsy and related diseases, sometimes the problem with the seizure is that the brain is experiencing sort of the equivalent of an electrical storm, if you will. And so if you have a miniature electrical storm in the left hemisphere of the brain, and then that electrical storm can kind of travel along the corpus callosum over to the right hemisphere of the brain, it just makes matters that much worse. Okay, so what I'm telling you is that in years past, not so much today, because we have newer medicines and newer technologies that can be used to treat seizure disorders. But in years past, 40 years ago, 50 years ago, if a person suffered from a severe seizure disorder, there's a very real good possibility that a doctor or surgeon would perform a procedure where you go in and you physically cut the corpus callosum. You cut it apart from each other, you separate it so that the electrical storm on one side of the brain is not able to travel as efficiently to the other side of the brain. Okay, so in years past, surgeons would cut the corpus callosum to try and treat seizure disorders that were caused by electrical storms in the brain. Now, that's an incredibly complicated topic, because at this point from chapter 7, you know that the electrical signal is due to this complicated motion of ions back and forth across the plasma membrane of the neurons of the brain. Well, imagine that that process becomes uncoordinated and chaotic in some way. That's basically an electrical storm, okay? And if you have that electrical storm, it can create muscular contractions and other seizure properties. Okay. Okay, gang. Any questions about the corpus callosum or cerebrum? Quinn, what was your question about the temporal lobe? We did put the temporal lobe in your notes. It processes your sense of smell. Okay, please, if you have another question, doesn't it also deal with hearing? Yes. Please understand, all these lobes that we've defined in figure 8.4, they're made of many, many cells that have overlapping functionality. So a subregion of the temporal lobe will process auditory information for hearing. That is true. Okay. All right. All right, folks. Let's move the conversation along here. Some other features of the brain I would want you to be aware of: the hypothalamus. Okay, the hypothalamus, take a look at that. You can see it's a very tiny section of neuronal tissue at the base of the brain there. The hypothalamus is a small cluster of cells that's heavily involved in a variety of processes that maintain homeostasis in your body, okay? So you can think of it as a mini computer within your brain that helps maintain homeostasis. Okay, a small cluster of cells at the bottom of your brain involved in maintaining homeostasis. And so, let me give you a quick list of some of the things it's involved with. The cells of the hypothalamus are influential in regulating your blood pressure. Okay, now please don't think that blood pressure is only controlled and regulated by the hypothalamus, because that is not true. That's not what I'm telling you. I'm telling you that the hypothalamus plays a role in regulating blood pressure, but there are other aspects of the body that do as well, such as the smooth muscle tissue around your arteries, okay? So the hypothalamus has something to say, something to vote on about blood pressure. It also it helps regulate your heart rate, your digestive activity, and your breathing rate, how fast you're breathing, okay? The hypothalamus, also, interestingly enough, plays a role in your sex drive and in the perception of sensations that include pain, pleasure, fear, and anger. Seems to be involved in sex drive, as well as sensations of pain, pleasure, fear, and anger. Of course, you ask yourself, well, how do we know that the hypothalamus is involved in your sensations of pain, pleasure, fear, and anger? Well, when you do studies in a controlled setting in a lab and you show somebody a scary picture on a computer screen and you have them hooked up to the right sensors and probes and so forth, you can detect electrical activity in the hypothalamus. That's not to say that other areas of the brain aren't also involved with these responses, but something about the hypothalamus is particularly important. At least we've been able to detect it with our studies. Okay, finally, I'd also like you to be aware of that it is the hypothalamus of the brain where the body's master biological clock is positioned. Within that small hypothalamus tissue there's a cluster of cells that are given a special name. They're called the cells of the suprachiasmatic nucleus. And that is the master biological clock of your body. Okay. Okay. Now, let me just mention something here. When you hear the word nucleus right now, what are you thinking about? When you hear the word nucleus, what are you thinking about? Okay. Thank you, Pete, a cell, and Emily, thank you, the organelle. Okay, fantastic. Okay, Quinn, the organelle that holds DNA. Good, fantastic, makes me happy. That's what you currently know the nucleus to be, right? The organelle inside the cell that holds the DNA. Well, like many areas in life, the meaning of a word is very contextual. In this conversation, in the nervous system, when you hear the word nucleus, it generally means a group of cell bodies of neurons, okay? So it doesn't mean the organelle here, it's referring to a cluster of neurons in the cell bodies of those neurons, okay? In this context, nucleus is referring to a group of neuronal cell bodies. Okay. All right. So just be careful, right? Like everything, we got to know the context of the conversation to be able to interpret the meaning properly. So what I'm saying to you folks, if you've ever had the experience that you went to bed one night and in the back of your mind, you knew you had a very important meeting or something you had to be up for the next day, there's probably a good chance you woke up even before your alarm clock woke you up. That was the suprachiasmatic nucleus doing its job. And it's also the suprachiasmatic nucleus that gets fouled up when you take a red-eye flight, and you kind of change time zones. It kind of messes up your body rhythm for a little while. The suprachiasmatic nucleus gets confused a little bit until that works itself out, okay? So please understand that your body has many clocks. In fact, okay, so I'm telling you about the suprachiasmatic nucleus in the hypothalamus of your brain. Scientists believe this is the master clock of your body. But please understand that every cell of your body does have the ability to perceive the passage of time. That might seem like a weird statement, okay? Let me stop sharing here, okay? Every cell of your body can perceive the passage of time. Think about that. That must be true, because is your body right now the same it was 10 years ago? No, okay, right? In other words, our bodies age and they change. And, those effects of aging become more prominent as we get older, and you have some magnificent things to look forward to in the future, I assure you. I'm being very sarcastic, okay? They're not magnificent, okay? So every cell of your body can measure the passage of time at a molecular level, okay? Do you have any questions right now? Okay, let's go back to our Word document here. We're doing pretty well, okay? I definitely want to see that we get through this chapter today. Okay, let's continue. So we've said something about the hypothalamus. I'm not going to talk about literally everything. There's just not enough time here. But let me talk about a few more things that are of interest. Let's talk about the cerebellum. Okay. The cerebellum, as you look down on the picture of page 130, well, I don't know about you, but when I look at the cerebellum, I think about cauliflower. Kind of looks like cauliflower, okay? But at any rate, this area of your brain called the cerebellum is responsible for your body coordination. Okay, there's a fancy word here that we're going to put in down as a vocab word. It's called proprioception. Okay, the cerebellum is responsible for your sense of proprioception. Okay, and proprioception is a fancy way of saying your body's, your brain's awareness. Proprioception is your brain's awareness of where your body parts are in three-dimensional space. Okay. Okay, so let me put that in parentheses here. Your brain's awareness of where body parts are in three-dimensional space. Okay, that is proprioception. All right, so, all right, just do me a quick, just humor me for a moment and do a little quick thing for me. As you sit wherever you are at this moment, okay, I would like you to just quickly, just close your eyes. Close your eyes. And without moving your head or doing anything unnatural, I simply want you to think of, do you know where your big toe on your right foot is at this moment in time? Without looking at your foot, without looking at it, without looking at your foot or your leg or your toe, and just closing your eyes, do you know where your big toe is? I suspect the answer is a definitive yes. You know where your big toe is because your brain is in constant awareness of it based on the nerve endings that are down your lower leg and into your foot and into your big toe. Those nerve endings are running signals up into the cerebellum and constantly giving your brain an awareness of exactly where your body parts are in three-dimensional space. You don't have to be looking at the body part. You still know, you still feel, you still sense where those body parts are. That's due to the information that your cerebellum is receiving from your body. Okay? All right. So at any rate, you know, your body, our bodies are amazing biological machines. We often take it for granted. I do too. I mean, there are moments when you have to take it for granted or you wouldn't get anything done. But think about, you know, your sense of balance, your sense of proprioception that the cerebellum provides to you, right? Don't we take it for granted that we can walk across the kitchen floor and not fall over while we grab onto the handle of the refrigerator, open the door, and pick out an apple or whatever it is we want to snack on, okay? That's not trivial, right? Try to design, build, engineer, and manufacture a robot to do that same kind of thing without falling over is really a lot of hard work, okay? So Mother Nature's really given us some amazing abilities that we kind of use and take for granted. Okay, let's continue here. Let me mention one more thing. Let me see here. One more thing. Okay, I'm trying to locate its location here actually in your book. Okay, page 134. Page 134 contains something called the reticular activating system. And I'd just like to make comment about this, okay? The reticular activating system. Number 5. Okay, the reticular activating system is not a defined structure. It's not like you can point to it on a picture and say, there it is. Okay, for example, wherever you are, you're sitting in a room filled with air, right? There's air around your body. So I could ask you to point to air, and you could literally point to any location around you and there would be air. Okay, so air is not really a defined structure because it's kind of everywhere at the same time. The reticular activating system is similar. It's not a defined structure that you can point to, but it is a network of neurons. It is a network of neurons, okay? This is a network of neurons that are known to do at least 2 things, okay? First off, okay, these neurons are responsible for keeping you alert and awake, okay? These neurons help stimulate other cells of the cerebral cortex to keep you alert and awake. Okay. So, you know, I would imagine there's times when we get into one of our discussions together as a group that maybe you're sitting there nodding off, your eyes are getting heavy. Well, there's multiple reasons that can happen, but certainly if for whatever reason you're not stimulated by our conversation, you know, it may be the fact that your reticular activating system is simply not stimulating your cerebral cortex enough and you're getting a little bit sleepy, okay? And there's something else here which I say tongue in cheek in sort of a comical way, but it does have a real practical application. The reticular activating system is also involved in filtering sensory information and prioritizing what gets fed to the cerebral cortex. So think of the reticular activating system also as a network of neurons that helps filter information and prioritize what gets sent to the cerebral cortex first. Okay, so it acts as a filter to help prioritize information and determine which information gets sent to the cerebral cortex first. So, okay, so let me ask you all something here, okay? Have any of you ever been in a room with somebody that was talking to you, but you honestly were ignoring that person? Such as you're watching something on television while somebody else is trying to get your attention and talk to you. Has that ever happened to you? Please raise your hand if you've ever ignored somebody. Okay. Please raise your hand if you were trying to talk to somebody that was ignoring you. Okay? All right. You see what we do to each other all the time. Okay? Well, your reticular activating system had a role to play in choosing whether you were going to ignore somebody or whether somebody was going to ignore you. Okay? And so that's part of the anatomy and physiology of what's happening. Now, in our conversation here, ignoring somebody in the living room might not be a big deal. I mean, you might get hollered at by your parents or your spouse, but not going to be a big deal. But think about it. What happens if you are driving down the highway and your reticular activating system decides that at that moment in time, it is more important for you to look at a text message on your phone than it is to look what's in front of your vehicle? You get what I'm going after here? This is a real safety issue for us in the modern world when it comes to cell phones and driving, because it is the reticular activating system that can get confused about the proper priority of information that your brain should be processing at a given moment of time, and it can lead to devastating consequences of car accidents and people dying because of it, okay? So it's your reticular activating system that plays a huge role here. Folks, do you have any questions right now? Okay, I'm as guilty as anybody for ignoring people and being ignored, but what I'm saying is, think about it the next time you want to look at a text message while you're driving. Do you really need to do that? Okay? All right. Okay, gang. So that's just a little bit about the anatomy of chapter 8. Certainly I haven't talked about everything, and there's things you're going to have to cover on your own time. I do want to talk a little bit about some nervous system disorders, give you a chance to ask some questions. Okay, Quinn, so when your father talks about politics, you just zone out? Is that what's happening? Okay, very good. All right. Okay, want to talk about a couple nervous system disorders. Okay, so let me go back to the Word document. Okay. Okay, we talked a little bit last time. I think it was last time we talked a little bit about some disorders that were associated with abnormalities in neurotransmitter levels, specifically, acetylcholine levels with Alzheimer's, and dopamine levels with Parkinson's, and serotonin levels with depression. So I'm not going to talk about those again, but let me just mention a couple things here that I'm sure we've all heard about. Some of us have experienced them. Okay. Okay. A stroke. Okay. Stroke obviously is extremely serious. Okay. When you say stroke, you're literally referring about the death of neurons. A stroke is a condition characterized by the death of neurons in the nervous system. Okay. When someone has a stroke, he or she has experienced a death of neurons. Now, obviously, that typically is caused by a lack of oxygen reaching that area of the brain. And there's many things that could disrupt oxygen. Okay, typically the oxygen levels are disrupted because there's a disruption to the blood supply, a disruption to the blood flow, right? So you could have, a blood clot form. Blood clot could stop blood flow. You could have a piece of atherosclerotic plaque break off inside an artery and block the flow of blood, which means the downstream tissue is not getting fresh blood, not getting fresh oxygen. The cells begin to die. That is a stroke, okay? Or you could have an aneurysm rupture. Okay. So we'll talk about what an aneurysm actually is in a future chapter, but can anybody tell us right now what is an aneurysm? Anybody know? What is an aneurysm? Okay, Alyssa, when you say a brain bleed, yeah, that's certainly going to be the outcome of a ruptured aneurysm. Okay. So obviously, if the brain is bleeding, the blood's not going where it's supposed to go. So the cells that needed the blood aren't getting it. So they're not getting the oxygen and they die. Okay. Folks, an aneurysm is a blood vessel that has overstretched. It's kind of like when you take a rubber band and you stretch it too far. When you stretch it too far, it may not come back to its normal size anymore because you've actually damaged the fabric of the rubber band. Blood vessels can work like that. If a blood vessel overstretches for whatever reason, then that's an aneurysm. And if that aneurysm, if that overstretched blood vessel ruptures, then you get a brain bleed, okay? So let me just put that in parentheses. An aneurysm is an overstretched blood vessel. Okay. All right, so obviously that's extremely serious. What can I say here about that? If you know anybody in your life that's had a stroke, please type yes into the chat window. Okay. Okay, Pete, you don't know anybody, so you're fortunate in that regard. Okay. I have known okay, I have known people in my life that have had strokes, right? We know that a stroke is very serious because when the neurons die, they are replaced with scar tissue, and the scar tissue does not function the same way as healthy neurons. And the ability of the brain to generate new neurons is very slow to not at all. Okay. Okay, Alyssa, thank you for sharing, right? Strokes are the real deal, right? And you need to take it seriously. My mother-in-law had a stroke about 5 years ago. And because she was too afraid to go to the emergency room right away, the consequences of her stroke were devastating, and she is now wheelchair bound because of it, right? So please, if you think somebody's having a stroke, even if they don't want to go to the doctor, please call for help, right? They need to get to the emergency room as quickly as possible. So Quinn, you asked what can cause a blood vessel to stretch in the brain? Okay, well, the reality of it is, folks, that we're all getting older. I know many of you are still, 18 or whatever it might be. But as we get older, the tissues of our bodies start to wear out. They start to slowly get damaged, and they get damaged enough that the body can't repair that. So as we age, our blood vessels, the elasticity in the blood vessels actually goes down. The blood vessels get less elastic, they're less stretchy because of aging. And over time, the blood vessel might get to a point that it doesn't stretch enough when the blood is pushed through it by contraction of the heart. And if the heart contracts and pushes a bunch of blood through that space and the blood vessel doesn't want to stretch, its only alternative is to rupture. Okay, all right. Okay, thank you, Jennifer. I'm glad that your husband was present. Okay, these are things that really do change your life very rapidly. Okay. Okay, so be careful with that, and always respond with an air to caution. If you're not sure, get help. All right. Okay, so we have the stroke, we have a coma. Okay, folks, we do not know a lot about comas, but I will say this, that a coma also involves damage to neurons, probably of the reticular activating system that are responsible for keeping your brain consciously awake. And so when you fall into a coma and you fall asleep in an unnatural state, what seems to be the case is that areas of the cerebral cortex that should be getting activated, that should be getting stimulated, for whatever reason, are not getting stimulated. We don't know why that is, right? If we knew, we could probably fix it enough to wake people up, but we can't. Okay, we can't do that. Okay, so coma also involves damage to neurons, in which cells of the cerebral cortex responsible for keeping you awake and alert are not receiving electrical stimulation. Okay. All right. Folks, do you have any questions at this time about stroke or coma or maybe other nerve disorders that you're curious about? Okay. All right. I'm not seeing anything, so we're going to put chapter 8 to rest. Again, there's going to be things in chapter 8 that you need to read on your own, because to keep up with our schedule, I will be starting chapter 9. Quinn, have people tried to artificially stimulate that part of the brain? Yes, Quinn, with limited success. In some people, they do start to arouse and become awake, but as soon as you take the stimulation away, the external stimulation, they fall back asleep. So, there's something broken biologically inside the person's brain to do that. Okay. Okay, Pete, I didn't know Elon Musk was working on that, but thank you. Okay. All right. Anything else? Yes, Alyssa. With medically induced comas, right, drugs are given to put a person into a deep artificial sleep, so that a person's body can heal from major trauma, like a horrible car accident or something like that, when the best thing for that person's body is to regenerate during an extended period of sleep. We do know enough about that we can medically induce it. Do medically induced comas cause long-term damage? I'm not aware of that, Alyssa. What I mean is by that, usually the coma is done to help a person. Usually if there's long-term damage, it's because neurons have been destroyed by whatever initial trauma happened to the body. But I'm not aware of medically induced comas causing long-term damage unless there's been a medical error administering the correct amount of a drug. Okay. Other questions? Okay, good questions. Keep them coming, because, at least by asking questions, I know you're engaged with the content, and that's really your pathway to success here. So good job with that. All right, folks, we are going to change gears here and now go into chapter 9 today. We're not going to get chapter 9 done, but I need to start it. Chapter 9 is about the sensory systems. Okay, so let's turn, if you will, to page 151, 152 in that area of your textbook. And we'll begin some notes on that. Chapter 9, sensory systems. Okay, well, before we get into the physiology of things, I need to define some terms for you that, in the context of what we're talking about here in our course, have special meaning. Okay, so let's begin with some basic definitions. Okay, the first phrase or term is going to be the phrase sensory receptor. Sensory receptor. Okay. Now, the word receptor, R-E-C-E-P-T-O-R, is a very contextual word in biology. Okay, and you're going to find receptor that means different things in different contexts. Okay, but in the context of the nervous system that we're talking about right now, sensory receptor refers to a structure that's made of specialized cells that include neurons that allow your body to detect changes in the environment. Okay, so a sensory receptor is a structure made of multiple cells including neurons that allow your body to detect and respond to changes in the environment. Okay. Probably the quickest and easiest, best example I can give you are the taste buds on the surface of your tongue. Okay. If you go back to the very end of chapter 9 on page 168, page 168, take a look at taste buds in figure 917. Okay. The taste buds that are on the surface of our tongues are drawn for you in a magnified version. And take a look at picture C. They're highlighting a taste bud there. Notice that the taste bud is made of things called supporting cells, taste cells, a taste pore, taste hairs, and the sensory nerves, which include the neurons that transmit information to your brain so you know what it is you're tasting. Okay, so all of those cells together build a structure that we call the taste bud, and the taste bud is an example of a sensory receptor. The thing about the sensory receptor is that no matter what it's made out of, it's always going to involve a neuron so that the nervous system is aware of what's happening. Okay, so let me just reference the example here of the taste bud. Okay, a taste bud is a sensory receptor, and you can look at that in figure 917. Page 168. Okay. All right. So that would be sensory receptor. Next term is going to be stimulus. Okay. A stimulus refers to any change in the environment that your body can detect, right? There could be changes in the environment that are so subtle in some way that your body's not aware of it. And in that case, yes, the environment is still changing, but since you're not aware of it, it's not a stimulus to you. Okay, so a stimulus is a change in the environment that can be detected by the body. Okay, and then we get even more narrow with the terminology here. The next term is sensation. Okay, sensation refers to your body's awareness of a stimulus. But hear me out here. Your awareness of a stimulus could be subconscious. Sensation does not imply a conscious awareness, because there are things that your body might be aware of subconsciously that you don't consciously know of. Okay, you're not thinking about it. Okay, so sensation refers to your body's awareness of a stimulus, but this awareness can be subconscious or conscious. Okay, so as an example of this, think about subliminal messaging, subliminal messages, perhaps in advertising, for example. Now, it's illegal to do subliminal messaging in advertisements today in the United States. You can't do it, okay? That being said, let me give you an idea here, okay? One common thing that psychology faculty like to do with undergraduate students is test them with subliminal messages. Okay, so as an example, imagine that we're watching a car commercial, okay? And let's say that the manufacturer of the car commercial, when you look at video, the video is made by individual frames of pictures being shown to you very rapidly, one after the next, right? So you might get 60 images every second, right? And so over the course of 30 seconds, you'll have 30 times 60 images shown to you to give you the impression of motion. Well, what if in 60 individual images, 59 of them are of a car, but one of them is of an ice cream cone? And so you watch this commercial for 30 seconds, and in that span of time, you have most of the images being that of a car, but a small portion of them being that of an ice cream cone. So that when you're finished watching the car commercial, you're not aware of the fact that you saw an ice cream cone, but after watching the commercial, you think to yourself, I'm hungry for an ice cream cone. I'm going to go get an ice cream cone now. Okay? So the image of the ice cream cone did not process in your brain consciously, but it did process and influence your brain in the sense that all of a sudden you have a hunger urge to go get an ice cream cone. That's subliminal messaging. Subliminal messaging would be an example of a subconscious sensation that your brain is aware of, but that you are not consciously thinking about. Okay, folks, does that make sense? Okay, all right. Okay. Think about subliminal messages in advertising. Okay, having a picture of an ice cream cone inserted into a car commercial. All right, that would be an example of a subconscious sensation. Okay, now, if you are aware consciously of a stimulus, if you have a conscious awareness of the sensation, then there's a specific term for that, and that is perception. You have a perception of it. Okay, perception refers to the conscious awareness of a sensation. Okay. All right, and then we have the phrase sensory adaptation. Sensory adaptation refers to a scenario in which your body is exhibiting a reduced or lowered response to a repeated stimulus. Okay, so this refers to a reduced response to a repeated stimulus, okay? As an example, imagine what it's like, well, okay, a couple things we could do as an example, right? You know, if you are a parent and you've had young children at the house, you know there's moments of time where the child just says, mom, 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 right? Or dad, 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 repeatedly, right? You might get to a point where you kind of just start to tune that little child out because all they're doing is saying your name repeatedly. That would be an example of sensory adaptation. Another example would be, okay, you open your window, you live in the country, you open your window and you smell the nice manure that a farmer's put down in the field. And in the first, in the first minute, it's so grotesque, you can barely stand it. But, 15 minutes later, you can barely smell it anymore. Now, it is possible that the odor drifted away because of the weather pattern around your house, but it's also possible that the odor is still present, but your body is simply not responding to it as intensely anymore because it's gotten used to it, okay? So that would be another example of sensory adaptation. So, example, getting used to a foul smell or odor, okay? All right. Folks, do you have any questions at this time about, yes, Pete, Stewie from the Family Guy. That's exactly right. Sleeping through artillery. Okay, good. All right. And farms. Yeah, okay, good, 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 good. So you folks know what I'm talking about. Okay, so there's lots of things we could talk about in chapter 9. And, I tend to gear my lecture to things that I think you are interested in, that I hope you're interested in. And so I'm going to start talking to you about your sense of vision. Okay, we are very visual people. Think about how much we rely on our eyesight every day to just get through life on a daily basis. Okay, so there's plenty of content in this chapter that you're going to have to do some reading on, but I'm going to try to give you some help with the topics of vision and hearing. Okay, so let's talk about vision as a topic on page 154 is where the topic starts. Okay, and so to talk about vision, we need to cover a little bit of eye anatomy. Okay, so vision, eye anatomy. Before we can talk about the physiology of vision, what it means to actually see something, we got to talk about the anatomy. Okay, the idea form follows function, right? Form follows function. If we don't know what the form is, we're not going to understand the function. Okay. Okay, so please use your eyeballs to look at the anatomy of the eye as I go over certain features that are explored on page 154, figure 9.5. Okay. The sclera. Folks, the sclera is the outermost layer of your eye, okay? And you can see that, in figure 9.5, when you look at that white tissue of that eyeball looking back at you from figure 9.5, that is the sclera, okay? The sclera will provide some amount of physical protection to the internal structures of the eye. And you probably know that the sclera is going to be the attachment point for your eye muscles, right? So when you move your eyes to the left, you're able to do that because there are muscles that are attached to the surface of your sclera. Okay, and you may have also known people that have lazy eyes and things like that, where their eye doesn't often stay centered very well. That's often caused by muscular defects or problems with the eye muscles themselves, or problems with how the eye muscle is attached to the sclera. Okay, so the sclera is the attachment site for eye muscles. All right. Next, we have the cornea. Okay, use your eye again. Take a look at the cornea. Cornea is a transparent, meaning it allows light through a transparent layer of tissue located at the very front of the eye. Okay. Obviously, if it's transparent, it allows light to enter the eye, so that's one function of the eye. The cornea actually has a shape that makes it curved. The cornea has a curved shape to it, and that curvature of the cornea actually helps to take light rays that are entering the eye and bend them in such a way to change their direction so that the light rays entering the eye actually start to focus back on the retina. Okay, so the shape of the cornea is important to allow light to enter the eye and change its direction in the correct way so it strikes the nervous system tissue at the rear of the eyeball. The curvature of the cornea helps bend light to strike the back of the eyeball correctly. Because if the light doesn't strike the back of the eyeball correctly, you may not see anything. Okay. And finally, I will also mention that the cornea, it may not be obvious from the drawing in your textbook, but the cornea is physically stitched. It is physically stitched, and together it is physically continuous with the sclera of the eyeball, right? So if you have the sclera and you go back a little bit deeper into the anatomy of the eye, you're going to find the cornea, okay? The cornea is physically stitched. It is physically continuous with the sclera. Okay, the cornea is physically continuous with the sclera. All right. Quinn, you ask, can people move a glass eye? Generally, no. Okay, generally, no. Okay, the reason, that would require a very sophisticated bionic apparatus to do that. Okay, a very sophisticated electrical equipment to do that. Okay, number 3. Okay, let's see, the iris of the eye. The iris of the eye is the colored portion of your eye that's behind the cornea. And the iris of the eye is important because it acts like the iris diaphragm of the microscope, but more appropriately, we should say that the iris diaphragm of the microscope acts like the iris of the eye, because Mother Nature invented it first, right? So the iris regulates the amount of light entering the eye. Okay. The light entering the iris is going to go through the center of the iris, which is actually given its own special name. That's your pupil, right? The center of the iris is the pupil. Okay. All right, folks, I'm going to try to roll along here so we can get this anatomy stuff out of the way so we can talk about some physiology next class. So please bear with me here. Number 4 is going to be retina. Okay, the retina is the nervous system tissue I talked to you a little bit about last chapter. Okay, this is the tissue of the eyeball that contains the photoreceptors that allow you to detect and respond to light. Okay, the retina is the nervous system tissue that contains photoreceptors. And you may remember from your high school day, there are 2 categories of photoreceptors. They are the rods and the cones. And if you're very curious, and you will encounter these as you read chapter 9, you can take a look. Probably page 160, figure 910 is going to have a drawing of the rod cells and the cone cells. Okay, we know that through experimentation and study over the years, we know that the rod cells are responsible for black and white vision. And we know that the cone cells are responsible for color vision. Okay. Also, if you are blessed in life with good health, we tend to ignore certain things because we have good health and we just take it for granted, right? But as you get older and you starting encountering health problems in a variety of ways, it's helpful that you are at least aware of these terms so that you can start thinking about things. Okay. The retina itself has a small cavity or pocket, or sometimes it's described as a pit. You can see that in figure 9.5, page 154, called the fovea. Okay, the fovea is a concentrated area of the retina that has an abundance of cone cells to provide vibrant, detailed color vision. Okay, in a subsection of the retina called the fovea, there is an abundance of cone cells to provide vibrant color vision. Okay, certain diseases that we could talk about, such as macular degeneration, sometimes diabetic retinopathy, they first become apparent to you that something's wrong because the fovea of the retina might become damaged. Okay, continuing here, number 5 is the optic nerve. Okay, the optic nerve is obviously the nerve. It's the bundle of neurons, specifically the axons of neurons that are bundled together and feed up into the brain so that your brain can interpret what it is detecting. Okay, what it is detecting, what light is being detected, and interpret that information. Group of neurons that connect the retina to the brain. Okay. As you know from last chapter, I'm talking specifically about the occipital lobe of the cerebral cortex. Okay. All right. Let's talk about some things here. Okay, let's talk about the lens of the eye. Okay, the lens of the eye, which you also see on page 154. Okay, this is transparent tissue that's located behind the iris, and the job of the lens is to provide additional focusing of the light that's entering the eye so it hits the back of the retina properly. Okay. So I'm watching our time here, but a couple things we need to talk about yet. First off, okay, what is the condition called when people have the lens portion of their eye start to become opaque in a way that light doesn't get through the lens anymore? What's that condition called? Okay, thank you, Matt. All right, yes, you got it. Okay, cataract. Okay, a cataract is a lens whose physical composition has changed, often due to aging, but sometimes due to disease, and it starts to block the transmission of light. Okay, so let's just put that down as a couple asterisks here. When a person develops a cataract, okay, cataract. When a person develops a cataract, this is a lens that has become opaque, meaning it blocks the passage of light. Okay. Yes, Gwen, right? It's very common these days. Fortunately, we do have the medical technology to usually successfully replace those with fresh artificial lenses. Okay. So a cataract's not too big of a deal, but you know, anytime you got to cut into the body, particularly your eyeball, to do it, there's a risk of infection. So you want to take any surgery, you know, even cataract removal, very seriously. Okay. And you know, that's why if you have two cataracts, you know, a reputable eye doctor is only going to do one surgery at a time, because God forbid you do two surgeries, two eyes on the same day, and there's some kind of problem and it causes you to go blind. That would be a horrible outcome. All right, so I do want to mention to you that there are two forms of liquid in the eyeball. Okay, so let's talk about those. Let's talk about the aqueous humor first. Okay, the aqueous humor, which, you know, you can kind of get an idea of what it looks like on figure 9.5 there. Okay, this is a clear liquid that's in between the cornea and the lens. Okay, it's a clear liquid in between the cornea and the lens. Okay. And as far as we can tell, the purpose of the aqueous humor seems to be to help create pressure in the eyeball, to help create the correct eyeball pressure, the intraocular pressure. Okay. And by having a correct pressure, you help maintain a proper spherical shape to the eye. Okay. So its purpose is to create the correct pressure so that the eye has a healthy circular shape. Okay. The aqueous humor is constantly replaced every day. Every day, our eyes remove old aqueous humor and replace it with healthy, fresh aqueous humor that the body's manufacturing. Okay, that's a normal thing that happens all the time. Okay, so in a healthy person, aqueous humor is continually refreshed. It's continually refreshed, meaning old is removed and new is manufactured. Now, here's where we get into another well-known disease of the eye, and that would be glaucoma. Okay, glaucoma is a disease of the eye where you have an elevated eye pressure. Okay, and there can be many causes for glaucoma, but the most typical one is that maybe there's some of the anatomy of the eye is not draining the old aqueous humor fast enough, and the body's continuing to make more aqueous humor than it should. Okay, so there's an imbalance between the old getting removed and the new being put into place. And so you get new getting pushed in and the old's not getting removed. And so that boosts the eye pressure. Okay. Folks, glaucoma is a silent disease. Okay, this is pretty serious. Okay, this is a silent disease. And what I mean by that is that frequently, if you have glaucoma, you won't feel it. It's going to be there, but you're not going to feel it. Okay, and that's bad, because if you don't feel it, you don't know that there's something wrong. Okay, so glaucoma is a silent disease, and it can cause damage to the anatomy of your eye, but most delicately, it can damage the retina of your eye. So this is a silent disease that often damages the retinal tissue in the eye. And for this reason, it is extremely, extremely important that you have an annual eye exam, because certainly in the early stages of the disease, you're very, very unlikely to feel that there's anything wrong. But while this is happening year after year after year, it's starting to damage your eyes in a way that cannot be repaired. Okay, so folks, it does not matter if you are 18 or 58. You should have an eye exam every year because of reasons like this. You don't have to be old to develop glaucoma. You can be young. People that are young and suffer with diabetes often have an increased rate of glaucoma in their eyes. Okay, so you can be a young person and still develop this disease. And if you don't get an eye exam every year to measure your eye pressure, there could be serious consequences down the road. Okay, so please, please, please get an eye exam every year. You know, there are other diseases that are silent. You know, glaucoma is a silent disease, and so is high blood pressure. High blood pressure is a silent disease. Okay, so when we get to that chapter, I'm going to harp on you about that. You know, please take your blood pressure routinely so you get used to what your blood pressure is supposed to be. Okay, folks, let me finish this topic, and then I promise I'll let you go. Okay, one last thing is the second liquid here. And so that would be number 8. Number 8 is the second liquid, which is the vitreous humor. The vitreous humor is a jelly-like liquid, okay? It's not as runny as the aqueous humor. It's more jelly-like in its consistency. It's a jelly-like liquid that's located between the lens and the retina, okay? Jelly-like liquid located between the lens and the retina. And folks, its purpose is not to maintain eye pressure. Its purpose is to hold the retinal tissue, to hold the retinal tissue in the proper location against the back of the wall of the eye. Okay, so its purpose is to help hold the retina tissue in place at the back of the eye. Okay, so there's another very serious condition, and I'll end with this one, which are, you know, detached retinas. Okay. Okay. A detached retina is a retina that has moved out of position from where it's supposed to be. Okay. All right. So, folks, I'm gonna stop sharing my screen. I'll be sure you get the notes, but let me just finish with this detached retina business a little bit. Okay. Detached retinas can be very serious. Okay. The retina, remember, the retina is nervous system tissue. It's made of neurons. And so it's extremely delicate. And so rather than being glued or attached to the back of the eye wall, it is gently pushed into position by the vitreous humor. Okay? So if you experience traumatic physical encounters, such as a car accident or something like this, you can actually slosh the liquid around so violently inside your eye that the retina starts to fall out of position. And if you have that, there's various grades of severity. If you have a partially detached retina, medical science can treat that and take care of you. But if you have a completely detached retina that is completely fallen out of position, you are going to be blind in that eye. You're never going to recover eyesight in that eye. Okay? So it's extremely important that, if you have a detached retina, that you seek medical care immediately. Okay? Let me say a couple things. If you love roller coasters, every year people walk off roller coasters with detached retinas. Okay? Usually they're partially detached retinas. But usually what will be is the case that you'll find that after the roller coaster, you might get some bad headaches, or you might see flashing kind of sparkly things in your eye area. If that stuff doesn't go away after a day, you should definitely see a doctor to make sure you don't have a detached retina. Let me tell you a little story. I work with a person who is having floaties in her eye. This goes back maybe 9-10 years ago. She was having floaties in her eye. She went to her eye doctor, and her eye doctor examined her eye and concluded that there was nothing wrong and that she simply needed a change in prescription for her glasses. So she got a prescription change and she continued to go about her business, but she still had the floaties and she was really bothered by this. Well, long story short, after months of this happening, she went and got a second opinion at a different eye doctor. The second eye doctor took a look at her eye and said, "Oh my God, you have a partially detached retina." The second eye doctor was so alarmed by what he saw that he was scared to move this person. He was scared to move this person to the emergency room of a hospital. He was scared that even the ambulance ride over might completely detach the retina and she would lose eyesight and be blind in that eye for good. So on a Friday afternoon, sitting in an eye doctor with a partially detached retina, the eye doctor stuck a needle through her eye and injected a stabilizing liquid to stabilize the position of the retina long enough that she could get more permanent medical care surgically at the hospital. And she did get that care, and it took weeks of recovery. When you have surgery on your eye, you are not allowed to watch TV. You are not allowed to read a book. You're not allowed to be on your cell phone looking at the screen. because all of that provides stress to the retinal tissue. You're not allowed to use your eyes. It's not a pleasant thing, gang. And like many things, glaucoma, detached retina, aneurysms, meningitis, you got to take these things very seriously. Okay, I know I'm over time. Let me talk about your homework. Okay, yes, thank God there's going to be homework today, right? I know. Okay, so lab on Thursday. Okay, we continue to be in this mode where we can't physically be together to do things. But here's the deal. On Thursday, we're going to go over as much of the content of Lab 5 as we can. If you have your lab manual available, go ahead and get it out. If not, I will include the instructions in my email this afternoon, okay? So, saw some folks migrate away, so I'll just pause a moment. Okay. For lab number 5, which begins on page 49, okay, on page 51, there's an activity called the patellar reflex. And the idea is that if we were together, you would partner up with someone and you would take a little rubber mallet that you've probably seen on the medical shows on television, and you would activate each other's patellar reflex by striking the tendon with the hammer. I know you don't have a patellar reflex hammer at the house, but here's the deal, gang. Okay, with your hand, touch your own kneecap. Touch your kneecap. With your fingertips on your kneecap, slowly move your fingertips down till the tissue becomes soft and you can push in on that tissue. That's your patellar tendon. Okay? So what I would like you to do is, with a family member that you can torture at the house, I would like you to try to activate their patellar tendon reflex, not by hitting them with a hammer. Please don't hit them with a hammer. But if my hand is the tendon, use your other hand like a karate chop and karate chop into that tendon to activate the reflex. Yes, you're going to miss it and people are going to complain and people are going to laugh, but do it anyway. Tell them that you have to do it as a homework assignment. Tell your wife that you got to hit her tendon, okay? Have some fun with it, and then let her hit your tendon. Let her hit your tendon, okay? So try to activate the reflex. And then there's a bunch of questions on page 51 and 52 to answer. On page 53, activity number 2, 2-point touch discrimination test. Folks, all you need to do is a friend, a brother, sister, mom, dad, wife, husband. All you need is a paper clip and a ruler, and you can do that at the house. Okay? So do that with a partner by Thursday's class. On page 56, activity 3 is the visual acuity test with the Snellen eye chart. Folks, today I'm going to send you through email your own version of a Snellen eye chart. You can print it out and you can tape it to a wall or a door and you can measure your visual acuity at home. Okay? So I will send that today. Activity number 4, the near point test. Folks, what it describes in your lab manual, all you need to do is need a book or a paper, something you can focus on with your eyes, and a ruler. That's all you need, and you can do it. Okay? So you can do that at the house. And folks, you've done everything in lab number 5. So have fun with this. It's meant to be fun. Okay? Hitting your little brother to activate the reflex should be fun. But we're doing this to understand the body and how it functions. Okay? So have fun, but take it seriously when it comes time to answer questions about what you're doing. Okay? Do you have any questions right now? Okay. Thanks for your time today. I'll see you on Thursday, okay? Take care now.